Hey everyone, welcome back to AP Precalc. This is lesson 2.15. Let's get right into it. All right, so here's the bell ringer for today. Pause the video if you haven't done this already because I'm about to go over the answer. So here we're just matching the graph to its description. So let's start with this one, exponential decay. That is going to be the one on right above it. A negative slope, that's linear. That's going to be the third one right here. Exponential growth should be the fourth one. And then a positive slope that's linear, that should be the second one right there. So that should be our answer to the bell ringer. All right, so semi-log plots is what we're going to talk about today. And so one thing that we've commonly seen with exponential data, and we saw it even before, if you go way back to the 2.1 video, when we were graphing, let's say we graph an xy thing, and we were graphing the equation y equals 2 to the power of x, and we had 1, 2, 3, 4, 5, 6, 7, right? Sure, you could graph 0, which is 1, 1, which is 2, 2, which is 4, and then 3 would be 8, and then 4 would actually like go off the page, right? And so that's one problem with exponential data is that it grows so quickly, it's so hard to encapture all of it in one graph where it's pretty hard to find the right scale, right? Do you make the scale by 5? Do you make it by 10? Do you make the scale even by 100 so then you can encapsulate some of the further data points along? And so what semi-log plots are, and what I'm going to introduce them to you as, is something that is really good for displaying exponential data. So what we're going to look at right now is a situation in which a semi-log plot is really useful. And so let's take a look at the graph on the left. This is modeling the population of English Americans in the US since 1620, where that's essentially going to act as our time zero. And we're looking at it from 1620 all the way to 1820, which is 200 years later. Right? The graph on the left shows the population using a normal scale for our x and our y-axis. So our x-axis, every tick mark is jumping up by 20 years, and for our population, for our y-axis, every tick mark is jumping up by 1 million people. And so this may look great, right? We know it's exponential. We know the data is exponential, and we see obviously it takes a little while for it to grow, but then after, around 1700, it starts to ramp up and jumps all the way up to 7 million. That's a lot that we can take away from that graph. However, there's one major problem that I see with this graph, and I'll point it out. The major problem I see with this graph is the fact that from around 1620 all the way up to like 1720, right? The first 100 years, all those points are almost indistinguishable, right? We can't pinpoint how many people were there in, 1680, right? And so the fact that we can't really notice a lot of differences in those beginning years is really a detriment to analyzing this data. And so this is where semi-log plots really come in handy. And this is what we see on the right. So this is an example of a semi-log plot where our x-axis is still normal, right? It increases by 20 every 20 years, every tick mark. However, our y-axis is going to be what we call logarithmically scaled. And what that means is every tick mark, instead of adding a million, right, or adding the same number, we are going to be multiplying. So here we start with 1, and then we multiply it by 10, and that's our second tick mark. Multiply that by 10, and 100 is our third tick mark, and then 1,000, and then 10,000, and then 100,000, 1 million, and then 10 million, all the way up to our final tick mark. And so this way we can see the pattern and kind of distinguish this a little bit more, but still know that it's exponential growth. And so this is a base 10 scale for our y-axis, right? On the vertical or y-axis. And so using a logarithmic scale allows us to view every single data point relative to each other. And that is what we're going to look at today. So first is going to be looking at the semi-log plot. You'll probably see a question or two on this on the AP Pre-Calc exam. So example 1, plot the following points on the same coordinate plane above. So here, there's a few differences with this compared to a regular graph that you're used to, right? First off, our x-axis is not going to change at all. We start at 0 here, and then you increase by 1, 1, 1, 1. That's great. Our y-axis is going to be very different. First, we don't start at 0, you start at 1, and then you increase, in this case, by multiplying by 10 each time. So times 10, times 10, times 10. In addition, these are not evenly spaced too, right? This is 2, 3, 4, 5, 6, 7, 8, 9, 10. And so obviously the closer you get to 10, the higher up you'll be because they want it to be proportional. And so let's plot the following points. 1, 20. So this is going to be 1 as our x variable, so right here. And then 20, 10 is right here. So 20 should be the next mark up because each jump is going to be 10. So this is going to be point A. This is 20, 30, 40, and then this right here is like 200, 300, 400. So now 2 comma 300 is going to go in the 2 column, and then 300 should be 100, 200, 300 right here. So this should be point B. C is 3 comma 2, so this is 1, and then going 1 up is right here, so that should be C. So remember, these are all jumps by 1. From here, jumps by 1. This is jumps by 10, and then these are jumps of 100. D is 4 comma 15. So 4, and then we go 10, and we know 20 is here. So 15 is going to be kind of around the middle, so that's where I'm going to put D. And then E is 5, 350. So 100, 200, 300, and then 400. So 350 should be somewhere in the middle. I'm going to mark that as my E there. All right, so let me erase some of the stuff there. So those should be our 5 data points for example number 1. All right, semi-log plots. So with the semi-log plot, the vertical or the y-axis, so it's always and only going to be the y-axis, is logarithmically scaled, meaning it might be, 10 to the first, 10 to the second, 10 to the third, or it might be a different number, but it's always going to be logarithmically scaled. And so the main thing here is with a semi-log plot, data that would typically show up as exponential like this is going to appear in a semi-log plot where it's, let's say, 10 to the first, 10 squared, 10 cubed. It's going to appear linear. And that is what a semi-log plot will do, and what we kind of saw with that population example earlier in the YouTube video. So, yep, this same example pops up again. 5 minutes ago, we looked at the 2 graphs displaying the population of English Americans from 16 to 1820, where we started at 1620. The graph on the left, right, shows the population using a normal scale on the vertical or y-axis. It increases by 1,000,000. And then let's take a look. The population on the right shows a semi-log plot where the vertical axis has been logarithmically scaled. And so example number 2, using the features of that semi-log plot, justify why we can assume that an exponential model is appropriate for the population of English Americans from 16 to 1820. And so here my answer would be, just looking at this, right? Seeing that this appears linear shows that the original data is going to appear exponential. So my answer would be, and this answers may vary here, an exponential model is appropriate because the semi-log plot above appears linear. And that would be enough for me for an answer. So because the semi-log plot appears linear, right, then that probably means the data is going to be exponential. All right, now remember, only exponential functions are used in semi-log plots, and are converted to look like linear lines in semi-log plots. However, the data is still exponential, right? So just remember, if you have exponential data, it's just a different way of viewing the data where it looks linear, but the data itself is still exponential. An exponential growth function will appear linear with a positive slope. Now, hopefully you can see why the bell ringer was what the bell ringer was. And then also, likewise, if you have an exponential decay function, let's say, let me come up with some better points here. If we have an exponential decay function like that, this is going to appear in a negative sloped linear line like that. All right, so those should be the two blanks in your notes as well. All right, for example 3, after Mr. Herkelman tells another one of my hilarious math jokes begins to spread around the school, the number of people that have heard the jokes or heard the joke after t minutes is graphed on a semi-log plot above. Which of the following could be the model for P? And so here, let's take a look, right? This is a semi-log plot. So we know that. We see it looks linear, which means that the data is going to be exponential. And so here we're probably going to want an exponential equation. So A, no, B is okay, C probably not, and then D is okay as well. So B and D are what we come down to. And now to determine what is our answer, let's take a look at one point. And these are actual points on the equation as well. And so this point right here is 0, comma, and not 1, but 2. So let's plug that in. We have 2 plus 2 to the power of 0, which this is 3. And then we have 2 times 2 to the power of 0, which is 2 times 1, which is 2. And so D is going to be our best bet, where B is not going to be containing that point of 0, comma 2 there. Important note about semi-log plots. When we logarithmically scale the vertical axis, we are not changing the actual data points, not even the y values. And so to logarithmically scale the vertical axis just means that here, for a regular graph, right, the x values are equally spaced, right, like +1, +1, and then the y values are also equally spaced on a normal graph. So we'll just say this is normal, and then we'll look at a semi-log plot. And so here, this is normal, right? Let's take a look at that example before, +1 million, +1 million, and so on, whereas in a semi-log plot, sure, our x-axis is still going to be equally spaced, +1, +1, +1, +1, but our y-axis is now going to be proportional. For example, times 10, times 10, times 10. And that's going to be what a semi-log plot is really all about. All right, for example 4, we are given a table that shows a few data points for function f, and we want to know which of the following graphs could represent this data in a semi-log plot where the y-axis or vertical axis is logarithmically scaled. So taking a look, there should be two that we can eliminate right off the bat, and that's because the vertical or y-axis is not logarithmically scaled. And those two that we eliminate are going to be A and C. If we take a look at A, right, it increases by 0.5 every time. That's a normal graph. That's not a semi-log plot. Same for C. It increases by 50 every time. That's going to be another normal graph and not a semi-log plot. For B, if we take a look here, this is 1, 2, 3, 4, 5. And then D, this goes like 1, 2, 3, all the way up to 10, 20, 30, right? And so on and so forth. So how do we know between B and D which one's correct? And remember, it has to contain these points. So let's just look at one point, right? We know the coordinate 1, 40 should be on the graph. And for B, we only know that this is 1, 1 point something, it doesn't really even matter what, it's like, let's say 1.8, right? That's clearly not 1.40 or 1 comma 40. So we can eliminate B. So D should be our answer. And just making sure, right, this is 1, and then 10, 20, 30, and then 40 should be that point that we see there. So D actually contains all those data points as well, making D the correct answer. All right, example 5. Plot the following points on the same coordinate plane above. So here we have 0, comma 200. So this is 100. This is 0. So 0, it's going to be in this column, and then 100, and this is 200. So this should be point A right there. B is 125, so 10, 20, and then this is 30. So it's probably going to be somewhere in the middle. So I'm going to put point B right there. C is 2, comma 7, so 2, 1, 2, 3, 4, 5, 6. Right there is C. D is 3.2, comma 80. So here, this is 5 equal ticks. So this is going to be 3.2, 3.4, 3.6, 3.8, and then 4. And so 3.2 should be that first tick mark, and then 80 should be 10, 20, 30, 40, 50, 60, 70, 80 right there. So that's going to be my best drawing for D. And then E is 4.6, comma 1.5. So again, it's going to go up by 0.2. So 4.2, 4.4, 4.6. And then this is 1, and this is 2. So 1.5 should be somewhere around right there. And so that should be E. We'll draw that dot again. There we go. And those should be those 5 points for example number 5. All right, so as we have seen, if we graph an exponential function, the graph should appear linear. However, in these cases, we can create a linear model for the graph on the semi-log plot. And so this is going to be how we form that equation to kind of get us a line of best fit on a semi-log plot. So if we are given the exponential model y equals a times b to the power of x, right, that's going to appear, or that's going to be exponential. And so what it will appear linear, and what is that line of best fit? That's going to be y equals mx plus b, where m is going to be this log base n b, and b in this case is going to be that y-intercept, which is log base n a. So this is b, which is your base b from right here. So it's important not to get these confused. And this is your b, like your y-intercept in the linear equation. And what is n, you may ask? N is going to be the scale that we are looking at for our y-axis. So for example, in the previous population example, our n would be 10 because it's times 10 times 10 times 10 times 10. Right? So that's our slope and our y-intercept there. And then b, or n, corresponds to the base used for the scaling. And it will tell you this in a question typically. So let's take a look here. A data set that appears exponential is modeled by this function, 8 times 3 to the power of t. The data is represented using a semi-log plot where the vertical axis is logarithmically scaled with the natural logarithm, right? So this is going to be log base e, or e is going to be our n value here, right? Which of the following can describe the appearance of the data in the semi-log plot? What is the slope and y-intercept? So first off, taking a look at this function, right? 8 times 3 to the power of t is exponential. So in a semi-log plot, this should be a positive slope linear. So positive sloped linear line is our answer to the first question. And then what's the slope and y-intercept? So remember our slope and then our y-intercept. Our slope is going to be log base e of b. In this case, b is 3, which is just ln 3. And then our y-intercept is going to be log base e of a, which in this case, a is 8. So this is just ln 8. So that is going to be our slope and y-intercept, and that's our answer to the second part there. All right, example number 7. A data that appears exponential is modeled by 7 times 8 to the power of t, and this is represented using a semi-log plot where the vertical axis is scaled with the natural log. So again, a base e. Which of the following could describe the appearance of the data in the semi-log plot? So we know the data itself is exponential, but in a semi-log plot, it's going to appear linear. So we can eliminate C and D right off the bat. And now we want to know, what is the slope? Is it 8 or is it ln 8? So here, for the slope of a semi-log plot, this is going to be log base n, and then in this form, a times b to the power of t, it's going to be b, which in this case is log base e of, in this case, b is 8, which is ln 8, and that should be our answer here. So B is our answer to example number 7. All right, so for the final example number 8, in a semi-log plot, which of the following pairs of functions appear linear as parallel lines? And so here, the only type of functions that you could even plot in a semi-log plot, at least for this class, is going to be exponential functions. So C should be the correct answer. However, let's take a look at those two functions, right? F of x equals 9 to the power of x, and g of x equals 2 times 9 to the power of x. What is our slope for each of those? Because if they appear linear as parallel lines, they should have the same slope. And so our slope here is going to be log base n, whatever our scaling factor is, and then in this case, our b value in the form from this exponential function is just going to be 9. For g of x, our slope would also be log base n, and then our b value is also 9 here. So they have the same slope. And so basically, whatever your base is, if your bases are the same, you're going to have the same slope. And then obviously our a values are a little bit different, and those affect your y-intercept. So that's why C is going to be the correct answer. If you guys have any questions, please come see me in office hours, and I will see you guys later. Thanks.